Hi there. A lot of folks seem to be confused on why are there sample versus population versions of various statistics like the variance, standard deviation, and covariance, but not for correlation. There is no population correlation and sample correlation. Well, in this set of notes, I'd like to explain to you why it is that if there were a sample correlation, it'd be identical to the population correlation. They've got to be the same thing. So a couple things to start off with. It's fairly common in statistics classes to draw a distinction between the population mean and the sample mean. But if you're ever working in Excel, you'll notice that the formulas are the same, right? You're just adding up all the values and dividing by n, and they'll have Greek letters versus x bar for population versus sample. They'll have a capital N for the population population size and little n for the sample size, but the formulas are identical. Now, when we're talking about variance and covariance, the formulas are a little different. Now, for population versus sample variance, you're looking at the difference between each observation and the mean, and then we're squaring that. And so that's common between both of these. The difference is that in the population, you're dividing through by capital N, by the total number of items in the population, whereas in a sample, it's n minus 1. Likewise for covariance, the numerators are the same, right? Especially if we realize that the means, whether you're looking at population mean or sample mean, are the same thing. The difference lies in that one you're dividing by n, and the other you're dividing by n minus 1. So the formulas are different, and for that reason, in Excel, they're population versions and sample versions of these formulas. But correlation is different. So for correlation, there's one formula in Excel and in your textbook. So why? Well, let's have a look. So here, I've got the population formulas. I have so population variance. I've got my nice little mean of x divided by the total population size, and for covariance, I've got that formula. Now, we start off with the definition of correlation. It's the covariance divided by basically the standard deviations of x and y. And if we substitute these formulas into the correlation function, what we'll get is the covariance of x and y in the numerator here, and plug in for variance of x and variance of y inside that square root, and we'll get these guys right here. And if we keep working and just substitute and just simplify, we can pull out a 1 over n from here. So we do that right here just by pulling out the 1 over n. But n is also here. We can pull out this n and pull out this n. So it's a product of two n's, so it's an n squared. And so that's our n squared. And then notice that we've got the square root of 1 over n squared. So it's like, what's the square root of x squared? It's just x. Well, what's the square root of 1 over n squared? It's just 1 over n. And so since this guy right here is 1 over n, then it cancels with that 1 over n. And it leaves you with a tidy little formula that doesn't have any of those divide by n's or n minus 1's. So just to drive the point home a little further, we'll do the same thing with the sample correlation. And so I've got here my formulas with x bars and y bars, and more importantly, I'm dividing here by n minus 1. And we can plug those into our definition for correlation, and we get here in the numerator, we got our n minus 1 bit here from the covariance, and then we just substitute in the sample variance for x and the sample variance for y, and then we simplify. So we can just pull this guy out. That's this guy here, right? And then we have this multiplied n minus 1 term. We've got two of them, so we can just kind of scooch that guy out. And then we've got the same thing that we had before. We've got the square root of something squared. So you can pull that guy out of the square root. It just becomes 1 over n minus 1. And then this 1 over n minus 1 cancels out with this guy here. And so what we're left with is, again, a tidy little formula for correlation that doesn't have the n minus 1s anymore, right? Those guys canceled. So if we just put these two formulas side by side, we have that the population correlation, a tidy little function, is equal to the same thing really as the sample correlation function. They look a little different. The only difference here is just notation, because we know that the average of x is the same whether we're talking about a population or the sample. So it's just that here we had 1 over n minus 1, 1 over n minus 1, and they canceled. Here we had 1 over capital N, 1 over capital N, and they canceled. So population correlation is exactly the same thing as sample correlation. So it's nice. One more reason to like the correlation. You don't have to worry about whether you're dividing by n or n minus 1. Thanks for listening.